Well, I think we should start this right now. I'm going to introduce myself. I am Paul Creeling. I am chairman of the East End Seaport Museum. If in these missives, so you've seen that you can join or you can make donations, please feel free. Always looking for membership. We're looking to create a more living organization here with volunteers and of course participants. Tonight's lecture is a virtual walk on the beach by John Holzapfel. Now, John has been a big friend of the museum for a long time, probably longer than I've been here. And he has been instrumental in all things marine biology here since his teacher, and I believe you pretty much started the beginning of the horticulture, the aquaculture out here. But John has a number of lectures. He lectures at Baconic Landing, the Orient Historical Society, all over, and Audubon Society. He is a font of information. I hope you all enjoy this program as much as I do. Again, I'm Paul Creeling from the East End Seaport Museum, and welcome all. Thank you very much.
Thank you, Paul, and the
myself.
East End Seaport Museum for inviting me to give this. I enjoy giving these talks, and I hope everybody else does. If you have questions, again, Paul mentioned, save them for the end, and we can put them at that. It's just a lot easier to do. All right, so as he said, we're going to do a virtual beach walk and some natural history. Can we get rid of those little charts on it by any chance, Steve? Okay, I'll keep going. Obviously, when we're doing, thank you. When we're doing a beach walk, we have to talk about beaches. Many of you will recognize Montauk Light. And if you look at the water, there's a nice, beautiful mist over it. And my point here is you see the boulders in the shore up here, and you can see the size of them. Now, those are being moved by the water, and that's the beach that you get at Montauk. That's called a high energy beach. So when you see big boulders like that, not the ones on the wall, but in the foreview, that means there's a lot of big energy waves coming in, and the sand and little pebbles won't stay there. And as you get down, the action of the water gets less and less. You can see here, you have stones of 1 inch or 2. Then sand starts moving in. And if we move over to the bay, we have a nice, soft sand. This would be a low energy beach. So you know you don't have lots of major waves. So the first thing to do is understand what kind of beach you're at. And again, it's fairly clear from one end to the other end. In between, you can estimate. Now, besides the beach being by itself, there's also movement of the beach. Here on the top, you see the summer profile. Now, in summertime, the winds in general, storms are less. And since they're less, the milder waves grab the sand from the bottom and slowly build up the beach during the summertime. So this is a natural progression that during the summertime, it slowly builds up. And then when the winter comes with the bigger storms, it's now washed back down offshore, and it stays there during the high energy winter waves. And the next year it'll come back. Besides going on and off, and this can be the problem, the sand is being washed out from, this is the Long Island Sound. You can see the cliffs and all the sand. The fine sand is mixed in there. And that's what's washing down, creating the beach also. But besides the on and off, there is the longshore current. And this is a general wind direction if you look down on the left-hand side. And this gentle wind is pushing down, and it can be a storm too. And it'll take the sand particles and move them in one direction generally. And if you go down to the beach, you can find out usually which way it's moving. I'll explain in a moment. But this is called longshore current, so that the sand moves along as long as the beach, the angle of the wind is hitting, the wind is meeting the beach at some angle. In this picture, I ask you first to look at the original shoreline. Ignore the line sticking out to it. That's the original beach. Now, when we put in a jetty, block that movement of sand, we have sediment building up on one side. Now, please understand, this is a model, a picture. In reality, those things should be at least 2.5 times the distance, the length of the jetty going out should extend 2.5 times to the next jetty at minimum to allow what you see on the bottom to occur. The ones in the diagram are just a little too close for that to happen. But you can see on the bottom picture that the sand does build up on one side. That's the updrift. Now, if I remove and just leave that last jetty or groin there, what's going to happen is that the beach will just wash away. It'll slowly but surely be taken away because there's no replenishment occurring. Again, this is the longshore transport, excuse me. This is a picture of Route 48. You can see on the bottom. There's a natural groin, natural rock revetment by the land itself. This is a point sticking out. But you can see at the very point that there are some rock revetments, groins here. And what happens is this blocks the sand from moving along, pushes it offshore. You can see this drift in here. And then right here, all of it starts going offshore, and this part is not being replenished. Now, if these people put a big jetty out here, they could build up their beach, and it goes on and on and on. You get the picture. So that's a little bit about onshore, offshore, and downward drifts. So you have a little sense of what a beach is about. Now I'm going to talk about a little bit about what you might find on the beach. And most of you should recognize that as a horseshoe crab. All right, Limulus polyphemus, the horseshoe crab. Now, I always like to say this, despite their name, horseshoe crabs are neither horses nor crabs. Unlike true crabs, which have 2 pairs of antennae, a pair of jaws, and 5 pairs of legs, are blue claw that you can see there. The horseshoe crab lacks antenna, lacks jaws, and have 7 pairs. So there's differences. They also have what they call book lungs, which are completely different from the way that the regular crabs. For your information, the horseshoe crab is much, much more related to spiders. They have a lot of characteristics that put them in the spider category. So they're not really crabs. In general, the blue shading here shows where you find horseshoe crabs. They live in deeper water. They come to mate and lay their eggs in the shallow water. Peak spawning occurs in New York, in our area on the island, in May and June, particularly during the evening high tides of new and full moon. What they're going to do is they're going to come in on a high tide. They'll lay their eggs, and then the water disappears, doesn't come back up to that height for another 2 weeks or maybe a month, and they're developing inside the sand. So that they time this mating at those real high tides. And if you want, go out the evening tide in particular. The evening tide is higher. And if you go out on May or June, one of those big high tides, go down to Halleck Bay, go down to the Sound, go down to your favorite beach, you might find a whole bunch of horseshoe crabs mating in a specific area. A male selects a female and then latches onto her. They have a little, males, if you look carefully, they have a pair of claws that allow them to latch on and hold on. The female digs a hole in the sand, lays her eggs, while the male is right behind fertilizing them. The male in general is smaller than the female. The female can lay between 60,000 and 120,000 eggs in batches of a few thousand. This is what a batch would look like. These are horseshoe crab egg clusters. And to give you some reality of what it looks like, there's 2 of them within a fingers. So you can see they're fairly small. Now, as I said, one of the things you might find on the beach are horseshoe crab shells. But please understand that's not necessarily mean that crab died. The larvae molt 6 times during the first year alone. They will shed their shells as they grow. So what they do is they crawl out of their shell. We'll see that in a minute. So this shows the first 3 or 4, they're planktonic, they're swimming, there's no tails to them. They eventually get the tail, they keep changing. And understand they have a hard shell on the outside. It's called an exoskeleton. We have an endo. Our skeleton is inside. Exo means it's on the outside. So there's no way, once that hardens, there's no way for them to get bigger. They can't crack that shell open. So what they do is they crawl out of the shell, inflate themselves with some extra water, and grow 10 or 15% each time. They usually molt around 16 times in the first 10 years. It is thought that the female may molt 1 year longer than the male, since their body size is usually a 1 size bigger. And here you can, whoops, let me not do, I didn't want to do that. Let me back up for a second. Now let me just, right here. This is the old shell. And this is the top of it. And the bottom is down here. And this is crawling out between the top. It'll leave all this behind. Every leg, every little antennae, the tail, and everything else. It's really neat when you find one of the shells to pry it open right here. And you can see inside. Yeah. Okay. Here you can see the shell. The old shell is being left behind. If you can see my pointer, the old shell is being left behind. The new one is crawling out. Here's the new shell. It's pushing out, pulling, and notice it's an exact replica of what it had. It's just 1 size bigger, 10, 15% bigger. Another interesting thing about horseshoe crabs is that they swim. Most people don't realize that. They crawl along the bottom, but they're quite good swimmers, as you can see in this film. Another interesting thing is their blood is blue. Our blood is based on iron. When you're short of red blood cells, you take iron because that's the central atom in a molecule of hemoglobin. Their central molecule is copper, and that gives a blue color to their blood. That little bottle is probably worth now $20,000 or $25,000 a piece. What they do is they bleed these crabs and they put them back, and they actually have farms or people who not raise them, but keep them year after year after year. They claim that 95% of them survive. Why it's so important is this is something that can be used to test the sterility of instruments. A lot of medical things use this as an indicator that there's sterility, and they use it throughout the world. The blue blood, inside it has special cells that attack anything, and they can have an indicator that shows something is not sterile without getting too complicated. Here you can see a mass of crabs. They're all laying eggs, and you can see here or there a bird, but more importantly, this is a little red knot. And if you look at the map, these birds migrate from South America to the coast of the United States, Maryland, Delaware, Virginia. They load up again and fly all the way up to the tundra to reproduce. Now, what do they feed on? What do they time their migration for? They look for the horseshoe crab's thousands and thousands of eggs. Evolutionarily, they've built that in to their trip. So without enough eggs to fuel them, the long distance flyers will have a tough time completing the last leg of their 10,000-mile trek from the southern tip of South America to their breeding grounds in the Arctic. And here you can see there's a horseshoe crab in the foreground, and all these birds are just devouring the eggs as they're in the shallow water. Just a neat little thing. It's a little bit of the natural history of horseshoe crabs. This, many of you again will recognize the common slipper shell, and its name is Crepidula fornicata. A neat scientific name. They have lots of other names: the slipper shell, the quarterdeck, the Atlantic slipper of limpet. There's lots of different names to it. The fornicata part of its name comes from the fact that these stack up one on top of the other. And there's an interesting arrangement to the way they're stacked up. If a juvenile, that's one floating around looking for someplace to go, lands on this stack, it develops and may remain as a male for an extended period, apparently maintained by pheromones released by females lower in the stack. So if one of these little guys that's floating around looking for someplace lands on the top, it becomes a male. If it misses and doesn't land on a stack, if it lands on a rock somewhere else, it changes from male to female. And it sits there waiting for the next available slipper shell to come and settle on top of it. And the one on top of it will remain a male. And the male actually has a long siphon that he brings around the shell and inserts into the female shell. Interestingly, if the female that's on the bottom of the stack dies, a male further up will change to a female. So there's a lot of things going on in those plain little slipper shells. Another thing you might find, as this picture shows, is the wing of a gull. You know, a bird has died for some reason, and it's sitting there on the beach. I just want to talk a little bit about what you can tell from that wing. This is a picture of the herring gull, an adult, completely mature herring gull with the yellow bill, the red spot, the bright eye, the yellow, the gray, and the black. The other gull that's common here, much less common than the herring gull, is the blackback. And the blackback is about 20% bigger, and it's not as common, but it's still here. So there's two different common species. We're going to talk about the herring gull. Often when I give my talks, I use the Orient Christmas bird count. And this is the last 25 years of the number of birds. And I know that not everybody understands. What they do here is Orient has a circle, and around Christmas time, give or take 10 days or so, a bunch of people, anywhere from 50 to 100 different volunteers, go out, and on one day they count all the birds they can. And these numbers are based not on the actual number of birds, but based on the number of people that are out there, the number of hours they're observing, and the number of birds. So it becomes a fairly constant thing over the years. So you can see, I think if you were to draw a line down through this data, you'd see that there is a gradual decrease. And according to the North American Breeding Birds Survey that they did in '66 and then 2010, there's a cumulative decline of 78% of these birds. Now, why that little bump is there, I don't know. It's some little project that somebody might want to try to figure out. But I then went back and showed 100 years of data. And this little part is the part I just showed you. And you can see the other part. Again, up until 1945 or so, the gulls didn't exist around here. They weren't around. We never found them. And then slowly but surely, they began to increase dramatically, held that population until the 90s. This is no factual basis at all, but my own personal sense is I wonder if this has to do with the garbage. In other words, after 45, this area began to build up. Garbage pits became much more common. The landfill was there. And then back in 90s and 95, they started to take the garbage away and limited the amount. It's just a theory. I have no evidence for it, but I just throw it out there. Now, again, here's a breeding male with all its glory. This is a herring gull. It takes 4 years to reach its adult plumage. And I just use this. It's something you can impress your friends and neighbors with someday when you're out on a walk on the beach. Juveniles have black bill, black legs, brown body, and secondary feathers, which give it a dusky appearance. Here's a first winter plumage. You can see it doesn't resemble those bright colors. There it is. So if you see something that colored, you can tell everybody that's a 1-year bird. That bird is only 1 year old. Next, a 2-year-old. Second winter birds are much paler. The key to this age is the adult gray back and scapulas and the brownish patterned wings. You can see it's starting to come out, but it's brownish. The base of the bill begins to pale, but it's still got a black tip, but you can see a little bit of yellow in there, and the eye color is starting to get brighter. So this is a 2nd-year bird, much different from the other one. And that's what it looks like in December. This is a 3rd-year bird. Now it's getting closer. The bill is turned yellow, but there's still a black spot. The eyes are brighter, darker. You can see the leg and eye color usually approaches that of a bird, but you can see the whiteness in it, the gray in the feathers. It looks almost like a mature one. So again, this is what it looks like at the end of the 3rd winter. So again, if you put this little mental picture, 1st year, 2nd year, 3rd year, mature, 4th year. So again, it's something that when you're going on your walk and you see a flock of gulls, you can say, oh, there's a 2-year-old, there's a 3-year, it's something to look for. It's kind of neat. It's interesting. They live for about 30 years, and some of them have been tagged over as long as 49, almost 50 years. So it's a long-lived bird. And again, if you need something to do in the cold, not that we're having a cold winter, The Herring Gull's World by Nico Tinbergen. Tinbergen was one of the 3 founders of animal behavior and Nobel Prize winner. And it's how the gulls talk to each other, what they say, their body sense, what they learn. It's a fascinating book. It's an old book, but it's really goes down to the basics and gives you a lot of good information. That's a little bit about gulls, what you might find on the beach. Next, we're going to talk about some shells. My favorite invertebrate, the bay scallop, Argopecten irradians. I'm going to give a little ad right now for Audubon. I'm going to give a talk in the next week or two called The Immense World. And it's based on a book that is on the New York Times bestseller, all about the senses that exist in all different animals. It's a fascinating book. And the reason I just bring it up here, it's going to be sponsored by Audubon, and you can go to their website and get invited to it. But the reason I bring it up here is that he spends about 3 or 4 pages on those little blue eyes, each one of the eyes. It's fascinating. They actually have 2 different kinds. They have 2 retinas, different retinas. One looks at motion, one looks at size of particles. And the evolutionarily, each retina comes from a different source, and they're all in that, each one in the little eye. It's a whole story. We'll talk about it some other day, but I just thought I'd mention it. The Immense World. These arrows point out a shell break or growth line. That line shows that the scallop is usually in its 2nd year and has spent a winter when the shell was not growing. If you think about it as rings of a tree, going from the bottom up, the first summer is when it grows all, and as the cold water starts to come, these animals are cold-blooded, so all of their chemistry starts to slow down, slow down, slow down. And when the water reaches about 40 degrees, it has basically stopped growing. It holds itself in abeyance. It's not hibernating, but it doesn't do a lot. And then when springtime comes, it starts to grow slowly again. And you get what's called a shell break. And you can see it in that. So if you see that in a shell, you can say, oh, that scallop is 2 years old. If you don't see it, you can say it's a 1-year-old scallop when you find it on the beach. I just thought that was a clear indication that the bottom part is the first year's growth, and the rest of it is the 2nd year's growth. They don't grow, they don't live longer than 2 years. And if you've never seen a scallop swimming, it's worth it. Notice it's jet propulsion. It's squirting the water out the back, not the front. And when it stops, it sinks to the bottom. This is our clam, our hard clam, Mercenaria. That's what a good, healthy handful of clams look like. Just for your own information, you often hear names, little necks. They're 1.5 to 2 inches. These are eaten on the half shell. Middle necks, 2 to 2.5. They're also eaten on the half shell, but they're also a baked clam. Cherry stones, now you got another 3 or 4 inches. These are baked clams, clams casino, such as that. And then finally, you have the chowders, the largest and toughest. Usually they wind up in soups. So you hear these words, at least now you have some idea what the words mean. This is a picture of a surf clam. Surf clams are fairly big. You can see the size of them. And as it says, you find them along the surf, particularly the oceans on the south side. But maybe about 20 years ago, somebody stirred up the bottom in Long Island Sound and found a few of these. And then somebody else said, oh, what a nice idea. And we ended up getting 3 or 4 trawlers that went back and forth along the north shore of Long Island from, I'm going to say, Wading River all the way out to Orient. And these 3 or 4 boats would go out every day, scrape along the bottom. And if you went into Mattatuck Inlet, there'd be 4 or 5 trailers leaving every day filled with these clams. And after 1 year or 2 years, they were all gone. So this is a surf clam. In here, you might look at this picture and say, oh, somebody's making a little chain, some artwork. No, it isn't. Those holes are from a natural predator. There's a structure called a radula. And that radula, just look, you can see the sharpness of the points. It goes back and forth. It rotates back and forth in this little animal, the moon snail. This is a predator, and it uses that radula back and forth. It actually injects a little bit of acid into at the same time, and it slowly but surely drills that hole, puts in enzymes, starts to digest the clam. And that's the moon snail. I got to say that 3 times. Moon snail shell that you often find on the beach. This collar is the reproductive organ of the moon snail. It's a sand collar. And what it does is mixed in with those sand grains is a mucus and also the eggs. And they blend it all together and it hardens, and this carries it along the bottom. Sometimes it gets washed up, often it stays on the bottom and they hatch out. It's a sand collar. Oysters, not as common on the bottom as you would normally see, but slowly but surely, I think they are making, there's so many, I'm going to call them boutique oyster companies. There's over 50 of them, I think now, that are out there growing oysters, and they are all putting off offspring. So I think you're going to see the numbers increase over time. But one of the famous things in oysters is that same similar hole. But this time it's done by what's called an oyster drill. Now on your screen, it might look like it's a foot long or 2 feet long, but it's actually about a 1/2 inch or 3/4 of an inch in size. And it has a radula, and it drills through and eats the oyster from the inside, basically. What you see on the left and right are those orange, they're the eggs of the oyster drill. Another shell that you often find is the blue mussel. They're usually, the mussels themselves are usually found in deeper water. So you have to be near a beach where it drops off fairly quickly. You can find them, they're around. The more common mussel shell that you find is the ribbed mussel. And that ribbed mussel is all over the marshes. It's what holds sometimes the sides of the marshes together. Another one that we find along the beach is the razor clam. This is just a picture of them. The neat thing about razor clams is they are extremely fast diggers. If you pull one out and you have them up on the top and put them on the sand, they dig right in front of you and go right down. They're like escaping from you. They're very, very fast. They put out a foot and drag themselves right down. So there's some of the common shells. These are 2 of the bigger shells. On the left is the channeled whelk, and on the right, the knobbed whelk, Busicon. And you can see the difference. The knobs, I'll show you a better picture here. On the left, it would be hard not to call that a knobbed whelk. In the middle, a channel. You can see the channel running right down. And on the right is the moon snail again, just to give you a sense of size. So these are 3. And again, this is what you might come upon. These are egg casings. And this is the egg casing of a channel whelk. Here you can see there's a great picture, and you can see it's producing these little containers of offspring. And in each of those, there's a bunch of baby little channel whelks. And there's a close-up. And the way you can tell it's a channel whelk is the edges of each individual capsule come together as if pinched. So you can see that they're tight along, it's almost like a purse on the bottom. That's the channel whelk. And on the other hand, this is the knobbed whelk. Do you see how there's a thickness to them? It's almost like a quarter, a large, edge to it. So again, you can impress your friends, neighbors, and relatives when you find one of these on the beach. If you see this flat edge to them, oh, that's the egg casing of a knobbed whelk. And the smooth would be the channel whelk. And here's a close-up of it. And again, in each of these, there are little baby whelks, as you can see in the next slide. This is just looking through. Now, again, if it washes up on the beach, they're all dead. But if it stays out on the bay bottom or the sound bottom, that they'll break apart, and those little guys you can see inside will start a new life on their own. And that's a little bit. Oh, one more thing. This is, you see a large pile of channel wells. Now, why are they all together? Why are they there? That's what you have when you're having scunguli. And there it is. You can see the shell right there and all sorts of different preparations of this wonderful treat. We're going to talk about a seaweed. This is an invasive seaweed. It appeared maybe 40 years ago, 50 years at the most. And it's called Codium dead man's fingers. It's a common name. Codium fragile is its scientific. And you can see on the left, it's attached to a muscle. And that's one of its problems, is that it will attach to a muscle. And then as it gets bigger and the waves take it, it pulls up the oyster, or it pulls up the muscle. And so it also has another name, the oyster thief. So it's known for attaching to an oyster, clam, scallop, whatever. And as it gets bigger and bigger, it prevents them from feeding easily. But more importantly, it can wash them up on shore. It's very buoyant, and as it floats with currents and waves, it can pull the shellfish to shore. Another algae that you see up on the shore, common. There's lots of them, and I'm not going to go through all of them, but some of them, fucus. Its common name is bladder wrack or bladder wrack. It's a seaweed found everywhere. North Sea, Western Baltic, Atlantic, Pacific, you name it. It's there, and it's a very common one. And you recognize it by those two little bladders where the arrow, they're dual bladders on each side of the main stem. And those bladders are used to float it. Now, again, seaweeds in general are plants, and plants, we all know, require sunlight. They take sunlight and they take carbon dioxide in the ocean dissolved in there, and they take the water, push them together chemically using the energy of the sun, and produce sugar and oxygen. So it's important that for this particular seaweed to get as much light as possible, and it does that by floating on the surface. It's a brown algae. It has other pigments in it. It still has chlorophyll, the green. All plants have chlorophyll. But this has some brown pigments, accessory pigments they're called, that help it get a little bit more light. It keeps the algae afloat. They are filled mostly with oxygen. That is the product of photosynthesis. Interestingly, in England, it was the original source of iodine discovered in 1811. And it was used extensively to treat goiter. Goiter is the disease of the thyroid gland, and it comes about from a lack of iodine. So if you look at the salt in your kitchen cabinet, you'll see iodized salt. The federal government 100 years ago or more said all salt companies have to add iodine so that nobody gets goiter. So it's actually put in there to make sure that everybody has a sufficient amount of iodine. The problem was people living on the shores, West Coast, East Coast, had enough fish in their diet and soil like that, but the people in the middle of the country weren't getting iodine. It could have been a problem. So they actually artificially introduced it. And another seaweed that you see, Chondrus crispus. Many people know it as Irish moss. And it's one of those things that have a following amongst the natural foods, and they claim it has all of these things: cough, healthy skin, connective tissue, soothes the digestive tract. It's used for a lot of different things, but it's also I'll talk to you. It's also used in emulsifying things like ice cream, cosmetics. Carrageenan is the chemical that they take out of the Irish moss, and they use it as an emulsifying agent. So it is actually harvested and grown a lot. This is the lady crab, and this is a live one, but many of you probably have seen this. And they're common along the North Shore beaches, something that you might find. This is an egg case, colloquially known as mermaid's purse or devil's purse. What is it? It actually surrounds the fertilized eggs of sharks and skates. About 40% of sharks produce their offspring by these mermaid purses. Sharks also bear young. They have little pups, but many of them, as I said, almost 40% of them produce these purses. And inside is a developing embryo. And again, this picture shows how that same sac has, if left not on the beach, but out in the water, you can see the organism extending, growing, and soon it will burst out of that and start a new life. So hopefully, whether you're young or old, you'll enjoy now a little bit more of a virtual walk on the beach. And I thank the East End for allowing me to do this. If there are questions, I'll try to answer them.
Share video. All right. Well, thank you very much, John. That was amazing. Most of the chats are just gee whiz. There is one from from Peggy with the Audubon website, www. Oh, let me read it off properly. www.northfolkaudubon.org. That will be your lecture in a couple of weeks. We also have another lecture coming up in a couple of weeks. We have the fish guy. I don't know if anybody knows Chris Paparo. He's doing a lecture right along the same lines as this, from plankton to whales. Why our local waters are worth protecting. I have seen this presentation. I truly recommend seeing it. You can go to fishguide.com or Facebook or whatever. You can see that he has a great love and respect for the area, just like John. Thank you again, John. So that will be on February 21st. Give it a couple of weeks in between. Again, I'm really looking forward to hosting you then. Any other questions? I'm looking here. The chat is pretty quiet. Great. Well, thank you very much, everyone. Talk amongst yourselves. All right.
Thanks again, Paul.
Take care now. Thank you.
Thank you, John. Thank you, everyone.
Thank you, John. Thank you, Paul. It was really
I wish
great.
you'd been my science teacher.
Thank you. It was
Yeah.
That's right.
Really
Thank you.
enjoyed it.
Beautiful photos too.
Yes.
Yep.
Thanks, everybody. I appreciate it.
Bye-bye.
Bye now.